Today, well, we've got quite a stack of sources here, all focused on the real sharp end of modern manufacturing. Our mission today is to unpack ISCAR's big new Logic Quick campaign. It's a whole launch focused purely on the latest innovations in turning tools. We want to distill what you really need to know about where this tech is heading. You know, when you think about manufacturing history, the lathe, the machine that does turning, it's arguably the oldest, most fundamental machine tool out there. It's ancient tech, really, but turning is still one of the most common operations done anywhere in the world. And because it's everywhere, even a tiny improvement in tool efficiency, well, it creates huge ripples, doesn't it, across whole industries?
Oh, absolutely. Huge ripples. And, you know, if you're looking for a kind of shortcut to understanding where component manufacturing is going, this deep dive is definitely it. We're going to lay out the 5 key directions that modern turning tool development is heading in right now. By the end, you'll have a really clear picture of what's driving efficiency, uptime, and, critically profitability in today's advanced factories.
Okay, let's get into it then. Before we look at specific tools, maybe the big picture, what are the main trends shaping all these new products? What are the themes holding this whole Logic Quick thing together? Why such a focus strategy right now?
Yeah, good question. We can definitely pin down 5 key development pillars here. The first one, and it's always there, is that constant push for higher efficiency and precision. So making the machining process faster, holding tighter tolerances, and of course, cutting down on waste and scrap.
Standard stuff, but always getting better.
Exactly. Number 2 is a really big investment in material science. Advanced cutting materials and progressive coating. They're constantly trying to push beyond the limits of, traditional materials like your standard tungsten carbide.
Okay, material science, got it. And the third pillar? That must link directly to keeping machines running, so versatility.
Precisely. Yeah, the third is multi-directional turning tools. So tools that can do multiple jobs facing, profiling, turning, without needing a tool change.
Okay.
That massively cuts down complexity, reduces downtime, less inventory needed. All good things.
Makes sense. What's number 4?
The fourth one is just essential for any modern factory setup. Digitalization. The cutting tool isn't just a lump of metal anymore. Its digital side is now absolutely critical for smart manufacturing for Industry 4.0.
Hang on, let's pause there a sec. Digitalization for a cutting tool, a piece of carbide. What does that actually mean for someone running the machine?
Right. It means the tool carries integrated data. Now, it might not have, say, a tiny sensor embedded in every single insert yet, but often the holder or the insert packaging has things like RFID tags.
Yeah.
Or it has digitally accessible data points about its exact geometry offsets, maybe its performance history, remaining tool life, that kind of thing.
Oh, okay.
And this data, it can be transferred instantly to the machine's CNC controller, or maybe the factory's main management system. It just makes setup and tracking way, way simpler. It means the smart factory knows exactly what tool is running, when it might need changing, how it's performing, all in real time.
Got it. That makes a lot more sense. Okay, and the 5th pillar?
And finally, number 5, which we'll definitely circle back to, is sustainability. Tools now really have to be designed to use less energy, generate less waste. It's about making sure economic gains are also environmental gains.
Okay, 5 key pillars. Now, you mentioned material science. That sounds really interesting. Pushing past traditional carbide, we're seeing ceramics and CBN, cubic boron nitride, mentioned a lot more in the sources we looked at. For a manufacturer who maybe still relies heavily on standard carbide, why make the switch? What's the real advantage of these super hard materials?
Yeah, it really boils down to 2 main things: heat and speed. When you're machining these modern, highly engineered alloys, think aerospace parts, medical implants, the process generates just immense heat.
Right.
Traditional carbide, well, it starts to soften and break down pretty quickly into that kind of heat. But these extra hard materials, ceramics and CBN, they keep their hardness and their edge durability even when things get incredibly hot. And that directly translates to superior cutting speed, much faster machining, and often much, much longer tool life.
Longer life, faster speeds. Makes sense.
And ISCAR is clearly pushing hard here. They've broadened their range of ceramic grades, targeting those difficult materials like hardened steel and cast iron specifically. But probably the most exciting thing detailed here is this new carbide grade they've introduced, IC10017.
IC10017. Okay, that sounds specific. You said it's for nickel-based superalloys. For listeners, maybe just quickly, why are those materials, the ones in jet engines, turbines, why are they so notoriously difficult to machine?
They're just brutal materials. They're designed to resist heat. They're incredibly tough. And crucially, they work harden almost instantly.
Work hard.
Yeah, as you cut them, the material right at the cutting edge actually gets harder because of the stress and heat, which, as you can imagine, leads to really rapid tool wear and generates even more heat. It's a tough cycle. So IC1017 was developed specifically to handle that hostile environment. It uses a high hardness submicron substrate. That means the core material, the carbide itself, has an extremely fine grain structure, which really boosts its toughness. And then it's combined with a very sophisticated PVD coating.
Okay, substrate and coating working together.
Exactly. And that combination finally lets manufacturers turn these really tough super alloys effectively, but at significantly higher speeds than they could before. This is a huge deal, especially with the demand we're seeing in aerospace and energy right now.
Okay, you dropped two technical terms there, PVD coating and submicron substrate. Can you break those down quickly for us? What are they and why do they matter for tool life?
Sure, happy to. So PVD stands for physical vapor deposition. The simple way to think about it is like painting the tool, but atom by atom inside a vacuum chamber. This process creates an incredibly thin, but very dense and very hard film on the insert surface. It's vital because it cuts down friction between the tool and the workpiece, and it acts as a thermal barrier, basically shielding the substrate underneath from the intense heat.
Right, protecting the core.
Exactly. And that core, the substrate, the carbide itself, that's where the submicron grain size comes in. Using really, really fine grains makes the carbide inherently stronger and much more resistant to chipping or cracking. That's absolutely key when you're dealing with the constant high-impact forces of turning superalloys.
So a tough core protected by a slick, heat-resistant layer. Got it.
Precisely. And just to add, they've also enhanced their tools for non-ferrous materials too, things like aluminum, copper, even platinum. They've got new inserts with a nanocomposite diamond-like coating. This is super specialized stuff, really focused on preventing material from sticking to the tool edge and ensuring you get a perfect surface finish on those softer metals.
That attention to specific material challenges is really clear.
Okay, let's shift gears a bit. Let's talk about pillar 3. Versatility and keeping the machines running as much as possible. Maximize uptime. What are the key products here designed to cut down on the number of tools you need for a complex part?
Right, that immediately brings the Quick T Lock family to mind. This tool really aims to change how turning is approached. It's designed for very productive, multi-directional cutting. What that means is it can handle front turning, back turning, complex profiling, facing operations, basically several different jobs with just one tool holder.
Without needing to stop and change the tool.
Exactly. The versatility itself is a massive time saver, and it simplifies inventory too. It also features a pretty unique insert clamping system designed for exceptional stability. You absolutely need that stability when you're pushing for high material removal rates.
Makes sense.
They've also built in an advanced chip former, which is specifically designed for high feed turning, and it's particularly good during backworking operations. Okay, hold on. Backworking machining. Can you clarify what that is exactly and why it needs a special chip former?
Sure. Backworking is when you're machining the rear face or maybe a shoulder on the part, essentially as the tool is moving away from the main spindle, perhaps towards a sub-spindle.
Oh, okay.
It's often used to finish features that are harder to get at from the front. But this movement can sometimes create issues with stability and especially with chip control. If the chip doesn't break cleanly and get out of the way, it can tangle up, damage the nice surface finish you want, or even break the insert.
Right, nasty stuff.
So the speckle chip former on the Quick T-Lock is designed to ensure those chips break reliably into small, manageable pieces and are evacuated cleanly from the cutting zone. This helps maintain quality and allows you to keep those high feed rates going, even in that potentially less stable backworking direction.
Okay, so it's like the Swiss Army knife of turning tools, but built for really heavy-duty work. We also saw mentions of the V-shape Cut V grip.
Yeah, those are interesting. They offer bidirectional external turning, so cutting in both directions along the outside of a part. And importantly, their V-shape lets them get into narrow grooves or tight machining areas where your standard V-type ISO inserts just physically can't fit.
So accessing tricky spots.
Exactly. And what's quite clever is their compatibility. Often, these V-shape inserts can be mounted onto existing tool holders, maybe with a slight modification.
Oh, that's smart.
It is. It means you can gain that multi-directional capability and get into those tight spots without necessarily having to scrap all your current holders and invest in a completely new set. It's a more gradual, cost-effective way to upgrade flexibility.
that makes good financial sense. Okay, let's pivot again. From flexibility to tackling some of those really specific, really annoying machining problems, let's talk about internal machining, specifically vibration when you're boring deep holes. That's always a headache, right?
Oh, vibration is the absolute enemy of quality in deep boring operations.
Yeah.
Yeah, huge headache. Anytime you have a long overhang, say, the boring bar is sticking out more than 5 times its diameter, to reach deep inside a part, vibration becomes a major issue.
And the results are?
Terrible surface finish on the inside of the bore, drastically reduced tool life because the insert edge is hammering instead of cutting smoothly, and it even spikes the power consumption of the machine unnecessarily. The traditional fix was just slow everything down, reduce your cutting speed, reduce your feed rate, which of course just kills your productivity.
Right, takes forever.
So the innovation here is really neat and, frankly, quite necessary. It's a new anti-vibration boring bar that has an active vibration damping mechanism built right into it.
Active damping, how does that work? Like electronically?
Not usually electronically, more like a tuned mass damper inside the bar. It's an internal mass, carefully designed and positioned, that essentially moves in opposition to the vibration. It actively counteracts and absorbs the vibrational energy during the cut.
Ah, clever mechanics.
Very. And the crucial takeaway for the user is this. You can now maintain high productivity. You can keep using aggressive cutting conditions, even with those long overhangs, without having to cripple your cycle time by slowing down. It's purely about protecting your output rate.
That sounds like a game changer for certain jobs. Okay, so that tackles challenges at the, let's say, the larger end of internal work. Now let's slide smoothly down to the other end of the scale, miniature parts. The Pico system. We know that's popular for small part machining, turning, boring, threading, little components. What's the newest development there, especially thinking about cost effectiveness for manufacturers making lots of these tiny parts?
Yeah. Pico system is well established for precision miniatures. But we need to think about the trade-off, between ultimate precision and manufacturing cost. The original Pico often uses solid carbide tools. They are incredibly precise, fantastic for finishing, but they can be expensive, and they're either disposable or costly to regrind accurately.
Right, high precision comes at a price.
Exactly. So the new option entering the market is Pico Index. What this is, essentially, is a system of steel and carbide boring bars, but they're specifically engineered to hold small, standard iso-indexable inserts.
Ah, indexable inserts like on larger tools.
Precisely. So what's the impact for the manufacturer? Well, you might sacrifice a tiny fraction of that absolute ultimate precision you could get from a perfectly ground-solid carbide tool. But what you gain is massive cost-effectiveness and flexibility, especially for the roughing and semi-finishing stages of making these compact parts. You use cheaper, indexable inserts for the bulk of the work.
So Pico Index is really aimed at high-volume production, where being able to quickly rotate or replace a cheaper insert edge is actually more valuable overall than chasing that last absolute micron of precision that the solid tool gives you.
That's exactly the idea. It lets manufacturers reserve those more expensive solid carbide Pico tools, maybe just for the final critical finishing passes. This drives down the total tooling cost significantly when you're removing the bulk of the material on thousands or millions of small parts. It's a very practical approach to managing costs in small part manufacturing.
Makes a lot of sense. Okay, this focus on high-precision applications naturally leads us to, I think, our final big innovation category, the dedicated focus on CNC Swiss-type lathes. Why are these machines suddenly so crucial that they're getting their own specific innovation push within this Logic Quick campaign?
Well, just look at the industries that are driving a lot of global growth right now. High-end watchmaking, yes, but also advanced medical devices, complex components for automation systems, electronics.
Tiny, intricate parts.
Exactly. They all depend on extremely precise, often miniature components. And Swiss-type lathes are the workhorses here. They offer incredible precision, partly because the material slides through a guide bushing, supporting it right near the cut. Plus, they can perform multiple operations, turning, drilling, milling, threading, often all at the same time in one single setup.
Very complex machines.
Very. So developing tools specifically optimized for these specialized machines isn't just nice to have, it's becoming a necessity to keep pace with the demands of these critical industries.
Okay, so what are the specific Swiss-type innovations under Logic Quickest?
Right, several key things. First, there's the Quick Swiss modular system. This is designed specifically for the subspindle area of the machine that's often doing backworking operations.
Yeah.
It offers easy height adjustment and, crucially, a quick change system with lots of interchangeable bases, holders, and cutting heads.
Modularity, quick change, Sounds like it's all about reducing setup time.
Absolutely. On these complex machines, setup and changeover time is incredibly valuable. Anything that speeds that up is a huge win.
Okay. And what about operations like grooving or parting off parts on a Swiss machine? Those need extreme consistency, right?
They do. And that's where the quick two-cut family comes in. These use narrow inserts, they're double-sided for economy, and crucially, they are mounted tangentially.
Tangentially, meaning from the side rather than flat.
Exactly. The insert sits sideways in the holder. The key benefit is that the cutting force is pushed directly back into the solid body of the holder, not trying to lift the insert up.
Much more rigid.
Much more rigid.
Yeah.
And that high rigidity is what ensures excellent dimensional repeatability, which is absolutely critical for medical parts, for example. You need every part to be identical. They've also integrated targeted high-pressure coolant delivery right to the cutting edge.
Why is that so important on Swiss machines?
Well, getting coolant effectively into those tight cutting zones is tough. Targeted delivery blasts chips away, preventing recutting, and it manages the heat very effectively. Both are vital for getting long tool life, and that perfect, pristine surface finish these industries demand.
Makes sense. Any other Swiss-specific developments?
Yes, they've also expanded their existing Logic 4 turn line. They've added smaller sizes of their indexable double-sided inserts. Again, it's about offering another cost-effective, high-performance tooling solution that's properly scaled and designed specifically for the tight confines of compact lathes and Swiss-type machines.
So it really feels like the theme here is making high precision, high volume work more economical, more repeatable, faster. And tying this back to that digitalization pillar you mentioned earlier, I noticed ISCAR actually added 2 new specific search filters to their online electronic catalog just for finding these Swiss-type modular adaptations. It seems like a small detail, but it feels significant, right? Recognizing that finding the right tool quickly and getting the setup data easily is just as important as the physical tool itself on these complex machines.
That's a great point. The digital infrastructure absolutely supports the physical innovation. Think about it. The speed at which an engineer or programmer can locate the exact right tool holder, the correct cutting head, download the precise offset data for a complex multi-operation job on a Swiss machine. That speed directly impacts the factory's overall profitability. It's all connected.
So looking back, we've covered a huge amount of ground today. I mean, from developing brand new materials like IC1017 to fight those brutal superalloys.
To implementing active anti-vibration systems for deep boring.
Right through to highly specialized modular tooling designed to feed the medical and aerospace industries via Swiss machines. It's quite a scope.
It really is. And the sheer breadth of innovation. From the fundamental material science all the way to very specific application-driven designs, it just shows that turning, even though it's based on an ancient process, is incredibly dynamic and far from stagnant.
Absolutely. So if we try to wrap all this up, I think the takeaway message for you, the listener, is pretty clear. That core operation, turning, it remains absolutely central to manufacturing globally. And the pace of innovation, it's definitely accelerating. The source material actually ends with a really direct challenge to the industry, saying essentially, you need to be quick to follow up on these new advantages in turning operations. Don't get left behind.
It's a strong message.
Yeah.